Hello friends, I hope you are doing well. I welcome you to the second part of solutions to past paper questions. This is Physics 9702, paper 4 A-level structured questions. We are still looking at ideal gases, temperature and thermodynamics to try and gain confidence with the questions as they are asked in this unit. So I hope you enjoyed part 1, and with your document in hard copy, you can easily follow. Do not forget to obtain and print a copy. It is free so that you can always follow from a hard copy document. Okay, so we had stopped on this question and I want to start with it again. We had stopped on this particular question, so let us start with it. A fixed mass of an ideal gas undergoes a cycle PQR back to P of changes as shown in the figure. Before you even see the questions, I want you to be able to analyze the figure. And you notice that we start from stage P and we come back to stage P. That means the initial temperature is the same as the final temperature is the same as the initial temperature if we come back to stage P. And if the initial temperature is the same as the final temperature, it means the total change in internal energy is going to be 0. Number 2, it is now volume on the vertical against pressure on the x-axis. Volume on the vertical against pressure on the x-axis. Let me try to make this thinner. Okay, so it's volume on the vertical against pressure on the x-axis. And also, here along PQ, you see that the pressure decreases from 8 to 2. The volume decreases from 8 to 2. And along QR, you see that the pressure, the volume remains constant. So here there is no work done. Here the work done is positive because it is resulting into a decrease in volume. And here the work done must be negative because it is resulting into an increase in volume. So at least you have that in mind. Okay, let's see the first equation. State the change in internal energy of the gas during one complete cycle, PQRP. So since the final temperature is the same as initial temperature, we have seen that T initial was the same as T final. So we can conclude that the change in internal energy, the total change in internal energy for one complete cycle is actually 0. Okay? Calculate the work done on the gas during the change from P to Q. What do we see from P to Q? There is a decrease in volume. The work done is going to be positive according to sign convention. The work done is equal to pressure times change in volume. So the pressure is, I think the pressure is here. The pressure is this one. I think this is 4.0. So the pressure will be 4.0 times 10 power 5 times 10 power 5 pascals. And the change in volume, the volume has changed from 8 to 2. So that is 6 times 10 power negative 4 meters cubed. And when you press your calculator, pressing the calculator, okay, pressing my calculator, this is 240 joules. That is 240 joules. So that was P to Q. So here I can write here plus 240 joules plus 240 joules. Then complete the table for the first row P to Q. The increase in internal energy. First law of thermodynamics, increase in internal energy will be Q plus work done. The work done is positive, 240. The heat supplied is negative, so we have 240 plus negative 600, and this gives us negative 360 joules. The second row, the sum of this is just plus 720 joules. Then the third row, remember here we say total change in internal energy if we come back to, for one complete cycle is 0. So when you sum up this row, we should come up to 0 because we have moved P to Q, Q to R, back to P. So the sum of this should be 0. And if you sum up this to be 0, this will be negative 360 plus 720 plus x is equal to 0. That means x is negative 360, so that you get the total increase in internal energy to be 0. Then moving backwards and substituting this formula, we have this as negative 360. We have Q as positive 480 plus the work done. So making the work done the subject, this gives us the work done as negative 840. Just make work done the subject. So that's how we come up with those values. Okay, next, state the basic assumption. The basic assumptions of the kinetic theory of gases. Those are 4 marks, so at least 4 points. State the basic assumptions of the kinetic theory of gases. Number 1, we always assume that the atoms are in continuous random motion. Atoms in continuous random motion. That's number 1. 2, we also think of a large number of atoms or molecules so that an average behavior is always considered. So we also say there is a large number. There is a large number of atoms or molecules so average behavior is considered. Number 3, we know that the intermolecular forces of attraction or repulsion are actually negligible. So we simply assume the intermolecular forces of attraction or repulsion are negligible. The intermolecular forces of attraction or repulsion are negligible. Intermolecular forces are negligible. Number 3, so the intermolecular forces are negligible. By the way, I said except during collisions. This was except during collisions. Number 4, we also said that atoms behave as hard, identical, perfectly elastic spheres. So atoms behave as hard, identical, perfectly elastic spheres. Perfectly elastic spheres. In other words, they experience elastic collisions. Number 5, I can add more. The volume of the atoms is negligible compared to the volume of the containing vessel. So total volume of atoms, negligible compared to the volume of the containing vessel. In other words, when you compare the total volume of all the molecules to the volume of the container, the H pi, you'll find the total volume of the molecules is negligible compared to the volume of the container. Those are 5. I can add one more. During collisions, not duration. Duration of collisions is negligible compared to the time between collisions. So duration of collisions is negligible compared to the time between collisions. So the duration of collisions is negligible compared to the time between the duration of the collision is negligible. I want to make this singular. The duration of collision is negligible compared to the time between collisions. So those are the basic assumptions of the kinetic theory of gases. We have question B. You may read through it first. So use equations for the pressure of an ideal gas to deduce that the average translational kinetic energy of a molecule of an ideal gas is given by that expression. So the equation for the pressure is always given the list of constants. In other words, they will always give you PV is equal to, they will give you PV is equal to 1 over 3 Nm mean square speed. But of course, we know that also PV is equal to nRT. PV is equal to nRT. And we know the number of moles is number of molecules or number of particles divided by Avogadro's number. That is number of moles times R times T. But we also know that R over NA is Boltzmann's constant, which is K. So this becomes N times K times T. So we now just equate the two equations. We simply equate the two equations. So we shall say a third N m mean square speed is going to be equal to N K T. So we simply, of course, N has cancelled out. You can see N cancels out both sides. N has cancelled out. N has cancelled out. So if N has cancelled, then we now remain with a third. Now I'm multiplying both sides by a half, so it will be a half m mean square speed. The other side also times a half, so it is a half k times t. So this is the mean squares, the average kinetic energy, the average translational kinetic energy. So we now have that EK, average translational kinetic energy, is going to be, we take through the other side to become 3 over 2 times KT. As simple as that. Okay, then part C, a deuterium nucleus and a proton collide. A nuclear reaction occurs represented by the equation as shown. We have a deuterium nucleus and a proton. State and explain whether the reaction represents nuclear fission or nuclear fusion. We remember nuclear fission, that was splitting. A heavier nucleus was splitting to give a lighter nuclei, or to give two lighter nuclei of approximately the same mass and relatively larger binding energy per nucleon. For nuclear fusion, two lighter nuclei were coming together to form a heavier nucleus of relatively higher binding energy per nucleon. When you look at this of course gamma is energy, this is energy. So state and explain whether the reaction represents nuclear fission or nuclear fusion. So I think you will realize that this is nuclear fusion because two lighter nuclei are forming a relatively heavier nucleus. So this is a fusion reaction. This is a fusion reaction because the reaction represents which the word should I use, build up. It represents build up of or making of a heavy nucleus. That is this one from light nuclei. From lighter nuclei. That is deuterium and a proton. Okay. So that is nuclear fusion. That is nuclear fusion. Okay, next. For the reaction to occur, the minimum total kinetic energy of the deuterium nucleus and the proton is 2.4 times 10 power negative 14 joules. That is for the reaction to occur. Assuming that a sample of a mixture of deuterium nuclei and protons behave as an ideal gas. If they behave as ideal gases, then the energy of each nuclei is approximately the same. So that means we shall say that the energy of one nucleus, the energy of one nucleus, the energy of one nucleus is going to be 2.4 times 10 power negative 14 divided by 2 because there are two nuclei. Okay. So the question is telling us to calculate the temperature of the sample for this reaction to occur. Temperature. So the proton and the deuterium nuclei will have equal kinetic energies. So the energy of one nucleus is given by that. So the proton and deuterium. Deuterium nuclei, the proton and deuterium nucleus will have equal kinetic energies. And therefore, we know that the average translational kinetic energy is given by 3/2 times kT. So we just consider one of them because we want to calculate the temperature of the sample of this reaction. If I consider, because this is for one nucleus and there are two, if I consider just one, so I will use half of their energy, total energy. So this will be 1.2 times 10 power negative 14 will be equal to 3/2. Then K, Stefan Boltzmann's constant, is 1.38 times 10 power negative 23, then times T. When I make T the subject, picking my calculator, just multiply this by 2, divide by 3 times 1.38, exponent negative 23. So T is 5.8 times 10 power 8 Kelvin. That is 5.8 times 10 power 8 Kelvin. You can check that temperature, but that is a vast amount of temperature. Next, suggest why the assumption made in part 2 may not be valid. Suggest why the assumption made in part 2 may not be valid. Maybe just to take you back, which assumption is made in part 2? In part 2, we have said for the reaction to occur, the minimum total kinetic energy of the deuterium nucleus and the proton is 2.4 times 10 power negative 14 joules. Assuming that a sample of a mixture of deuterium nuclei and protons behave as an ideal gas, calculate the temperature of the sample for this reaction to occur. Now, the assumption that these behave as an ideal gas is extremely wrong because the two nuclei have the same positive charge. They are most likely going to repel. And if they repel, the force is not negligible, so they cannot be considered to be behaving as ideal gases. So here, intermolecular forces exist. So the assumption may not be valid because intermolecular forces exist. So we are saying intermolecular forces exist. Intermolecular forces exist since the proton and deuterium nucleus the proton and deuterium nucleus the proton and deuterium nucleus are positively charged they repel each other. So the proton and the deuterium nucleus, these are both positively charged, so they will have to repel each other. Okay, next. One assumption of the kinetic theory of gases is that gas molecules behave as if they had elastic identical spheres. Let's do other assumptions. We have mentioned many. I'll just mention a few for now, since we have now mentioned many. Number one, the time of collisions is negligible compared to the time between. Time of and the time between. So time of collisions or duration of collisions. Time of collision is negligible compared to the time between collisions. Number two, we have said no intermolecular forces, no intermolecular forces, no intermolecular forces of attraction or repulsion. Number 3, we mentioned that the molecules move in rapid random motion or the molecules are in continuous random motion. So I will simply say molecules move in rapid random motion. The molecules move in rapid random motion. We also say that the volume of the molecules themselves is negligible compared to the volume of the container. Total volume of molecules negligible compared with or compared to the volume of the container or containing vessel. Total volume of the molecules themselves is negligible compared to the volume of the container. Also, we always assume that there is a large number of molecules. There's a large number of molecules, so an average behavior is always considered. So you can't fail to state 2 from all those ones. Using the kinetic theory of gases, it can be shown that the product of the pressure P and the volume V of an ideal gas is related by that expression. State the meaning of the symbol N. N is the number of gas molecules. N is the number of gas molecules. Then this one is familiar. We are now familiar with this. This is the mean square speed. The mean square speed of gas molecules or of a molecule. Okay, I think that is obviously good. Use the expression to deduce that the mean kinetic energy of a gas molecule at temperature T is given by that. At this point, this should now be something we enjoy playing with because it is obvious. PV is equal to a third Nm mean square speed. But we know that PV is equal to nRT. We remove N, that is number of molecules, divided by Avogadro's number, times R times T. When we know R over NA is Boltzmann's constant, so this is NK times T. So that means we now equate PV is equal to NKT to this value of PV, so a third Nm mean square speed is equal to NKT. Multiply, of course, N has cancelled, multiply both sides by a half. So you have that a third into a half M mean square speed is equal to a half K times T. This one here is the the average kinetic energy EK. And when you multiply both sides by 3, it becomes 3 over 2 times KT as required. Okay, next. State what is meant by the internal energy of a substance. This is the sum of the random distribution. The sum of the random distribution the random distribution of potential energy and kinetic energy of all the molecules which make up the substance. Use the equation in B Roman 2 to explain that for an ideal gas, a change in internal energy delta U is given by change in internal energy is directly proportional to the change in temperature, where delta T is the change in temperature. So remember that the internal energy of a system is equal to the kinetic energy plus the potential energy of the molecules. But if the gas is ideal, there are no intermolecular forces. So for an ideal gas, no intermolecular forces. And the potential energy depends on these forces. So we say that there is no potential energy. There's no potential energy. So that means any change in internal energy will equal to change in kinetic energy. So change in potential energy, in internal energy, any change in internal energy will be equal to change in kinetic energy. Of course, the change in kinetic energy is directly proportional to temperature because temperature is the average kinetic energy of the molecules. So the change in internal energy is equal to a change in kinetic energy, and this is directly proportional to change in temperature. Okay, I think that is fine. Again, the mean translational kinetic energy of a molecule is given by that expression where T is the thermodynamic temperature of the gas and K is the Stefan Boltzmann's constant. Determine the value at which the root mean square speed of hydrogen molecules is equal to the speed calculated in B. Now here I removed B because it was too much repetition. So I'll just quote the root mean square speed obtained in B. So in B, the root mean square speed we calculated in B is 5.03 times 10 power 3 meters per second. In B, which is missing here, the root mean square speed is 5.03 times 10 power 3 meters per second. Using that value, we should be able to get the temperature at which the root mean square speed of hydrogen molecules is equal to the speed which has been calculated to be this. So we just use the expression. The average kinetic energy is 3 over the average kinetic energy is 3 over 2 times K times T. So this will be 3 over 2 times K, which K is 1.38 times 10 power negative 23 times T. This should be equal to kinetic energy, which is a half, times the mass, which mass is, they have given us a molecule of hydrogen has a mass of 2U, so this would be 2 times 1.66 times 10 power negative 27 to change it to kilograms, times the speed, which is, this was the root mean square speed, so it means the mean square speed will be 5.03 times 10 power 3. This is squared. I'm just substituting in EK is equal to 3 over 2 KT, which is the same as a half m mean square speed. I pick my calculator. You can also pick yours and verify. I'm finding T. So finding T, this is giving me 20, around 2030 Kelvin. 2030 Kelvin as the temperature. Then part 2, state and explain one reason why hydrogen molecules may escape from Mars at temperatures below that calculated in Roman 1. Why would hydrogen atoms escape from Mars at this temperature? First of all, remember, according to the kinetic theory, there is a range of speeds. So some molecules could be having higher speeds, higher than the one that we have calculated in part B. So we can say since there is a range of speeds, some molecules have higher speeds or could be having higher speeds. So that means they have higher kinetic energy, so they would escape. That's number one. Alternatively, you could also think about some molecules escaping from a point just above the planet's surface, rather than just on the surface. So it means they would be having a higher initial potential energy than they would have when they are at the surface. So some molecules escape from a point above the planet. Above the planet's surface. This means the initial potential energy is higher. So the initial potential energy is higher. Okay. Next, a resistance thermometer and a thermocouple. Thermometer are both used at the same time to measure the temperature of a water bath. Explain why, although both thermometers have been calibrated correctly and are at equilibrium, they may record different temperatures. First of all, we said if these are operating on a centigrade scale, the centigrade scale is calibrated assuming linear change with the temperature, but neither properties vary linearly with temperature. Neither resistance nor thermoelectric EMF varies linearly or perfectly linear with the temperature, as it is assumed during calibration. So we say temperature scale is calibrated. Temperature scale temperature scale is calibrated, assuming linear temperature scale is calibrated assuming linear change, with the temperature, assuming linear change with the temperature, but neither property varies linearly with the temperature. So during calibration, they are always assuming that the properties vary linearly with the temperature, but in practice, neither of the properties vary perfectly linearly with the temperature, as it is always assumed to do. That's why I said, but neither property varies linearly with temperature. Okay, we can proceed. State in what way the absolute scale of temperature differs from other temperature scales. Of course, we know that the absolute scale does not depend on the property of a substance. So this one does not depend on the property of a substance. It doesn't depend on any property of a substance. That's why we call it absolute. What is meant by absolute zero of temperature? What is meant by absolute zero of temperature? Remember, temperature is the average kinetic energy of molecules that make up the system. So that means the temperature depends on the kinetic energy of the molecules. That is if the temperature is in Kelvin units. But then when we talk about absolute zero, then it means the average kinetic energy of the molecules is going to be zero. So absolute temperature is the temperature at which atoms have minimum or zero kinetic energy. The temperature at which atoms or molecules have minimum or zero kinetic energy. So that's what we call absolute zero. Remember, if the average kinetic energy EK is equal to 3 over 2 K times T, at absolute zero, this value here, T, is going to be zero, meaning that the kinetic energy will be zero. That's what we are referring to as absolute zero. Okay, next. The temperature of a water bath increases from 50 degrees Celsius to 80 degrees Celsius. Determine in Kelvin and to an appropriate number of significant figures. The temperature 50.00 degrees Celsius. So since this is given in decimal places, we shall use 273.15. So this will be 50.00 plus 273.15. It is given two decimal places. I will quote the answer to two decimal places, and this is 323.15 Kelvin. Then the change in temperature of the water bath. Change in temperature of the water bath. That is difference. Remember, a change in temperature on the Kelvin scale is the same as a change in temperature on the degrees Celsius scale. So we shall have 80.00 degrees Celsius minus 5.00 50.00, and this gives you 30.00. So this is 30.00 Kelvin. Okay, number next. A student suggests that when an ideal gas is heated from 1000 degrees Celsius to 200 degrees Celsius, the internal energy of the gas is doubled. The internal energy of the gas is doubled. State what is meant by internal energy. Internal energy is the sum of the random distribution of the kinetic energy and the potential energy of all the atoms, molecules, or particles which make up the system. The sum of the random distribution of the potential energy and kinetic energy of all the molecules or particles, or it can be atoms, which make up the system, which make up. So that one is internal energy of a system. By reference to one of the assumptions of the kinetic theory of gases and your answer to Roman 1, deduce what is meant by internal energy of an ideal gas. Reference to one assumption. The assumption of this is no intermolecular forces. So no intermolecular forces. Then no intermolecular forces between molecules, no intermolecular forces of attraction or repulsion. And if that is true, if there are no intermolecular forces, so we say that there is no potential energy. And if there is no potential energy, then it means we now remain with only the kinetic energy component. So internal energy is solely, that is, it is only kinetic energy of the random motion of molecules. So the internal energy is solely or only the kinetic energy of random motion of molecules. Okay, so next. State and explain whether the student's suggestion is correct. So a student suggested that when an ideal gas is heated from 100 degrees Celsius to 200 degrees Celsius, the internal energy of the gas is doubled. The internal energy of the gas is doubled. However, remember when we were defining temperature as the average kinetic energy of the molecules, this was only on the Kelvin scale. So kinetic energy is directly proportional to absolute temperature, not temperature in degrees Celsius. Kinetic energy is proportional to Kelvin temperature or absolute temperature. But the Kelvin temperature we can check if it is doubled. So we are changing from 100 degrees Celsius. 100 degrees Celsius is the same as 273 plus 100, which is 373. Then 200 degrees Celsius is the same as 200 plus 273, which is equal to 573. No, 473, I guess. 200 plus 273, that is 473. And you notice that this is not doubled. So temperature in Kelvin is not doubled. Temperature in Kelvin units is not doubled. Temperature in Kelvin is not doubled, so the suggestion is not correct. Temperature in Kelvin is not doubled, so the suggestion is incorrect. The suggestion is incorrect. Or you would think of the temperature. The temperature is in Celsius, not Kelvin, so it is not correct. Kinetic energy is proportional to absolute temperature. That is temperature in Kelvin units. If temperature in Kelvin units is not doubled, then we cannot believe that the internal energy is doubled, because the internal energy is dependent on the kinetic energy of the molecules. So kinetic energy is proportional to absolute temperature, and temperature in Kelvin is not doubled, meaning the kinetic energy is not doubled, therefore the internal energy is not doubled. So the assumption or the suggestion is incorrect. Okay, if that suggestion is incorrect, then we can continue. State what is meant by thermal equilibrium. Thermal equilibrium. Thermal equilibrium, we said when thermal equilibrium is established, the temperature of two parts of a body is constant. The temperature of two parts is constant. Now here we have two metal spheres that are in thermal equilibrium. So it means the temperature of the spheres is the same. So temperature is the same. Temperature of the spheres is the same. And if the temperature is the same, there is no net transfer of energy between the two spheres. No net, this is very important. No net transfer. There is no net transfer of energy between the spheres. There is no net transfer of thermal energy between the spheres. Okay. Next, an electric water heater contains a tube through which water flows at a constant rate. The water in the tube passes over a heating coil. I think we called this one the continuous flow method. The water flows into the tube at a temperature of 18. Here it is 18. When the power of the heater is 3.8 kilowatts, the temperature of the water coming out is 42 degrees Celsius. The specific capacity of water is this. Remember, note that is joules per gram per Kelvin. Use the data to calculate the flow rate. That is the mass flowing per unit time of water through the tube. Okay, so the amount of heat supplied goes into raising the temperature of the water. This is given by power times time, which is going to be given as the mass times specific heat capacity times the change in temperature. So when I divide by T, this is going to be by T by T. So M over T is going to be mass per unit time, that is the flow rate. So the rate is going to be equal to power divided by specific capacity times change in temperature. The power has been given as 3.8 times 10 power 3 divided by the specific heat capacity, which is 4.2, then times specific capacity is 4.2 times the change in temperature, which is 42 minus 18. 42 minus 18. Because our mass flow rate is in grams per second, I don't need to change the specific capacity. So we can now simply divide this, press the calculator. So this is giving us 38 to two significant figures, that is 38 grams per second, that is the flow rate. Okay, next. State and explain whether your answer in Roman 1 is likely to be an overestimate or an underestimate. I think it is most likely going to be an overestimate because some thermal energy is most likely going to be lost to the surroundings. So whatever we obtain is an overestimate. So some thermal energy is lost to the surrounding. Some thermal energy. Some thermal energy is lost to the surrounding. Some thermal energy is lost to the surrounding. To the surroundings. So the rate we have estimated is an overestimate. Not all the thermal energy supplied goes into changing the temperature of the water. So the rate we have obtained is an overestimate because some thermal energy is lost to the surrounding. Okay, next. The product of pressure P and volume is given by that expression. State the meaning of N. I think this is obvious. Number of molecules or total number of molecules. Total number of molecules. Then this is read as the mean square speed. The mean square speed of a molecule or of molecules. The mean square speed of molecules. Okay, next. The product PV is also given by PV is equal to NKT. Deduce an expression in terms of Boltzmann's constant K and the thermodynamic temperature T for the mean kinetic energy of a molecule of an ideal gas. So we have two expressions here that we can simply equate. We have PV is equal to NKT and PV is equal to a third NM. So I am just going to equate these two. So I will say that a third NM mean square speed is equal to Nk times T. N has cancelled out. I multiply both sides by a half, so this will be a third into a half small m mean square speed. This will be equal to a half kt. So when I make, of course, a half m average c squared is kinetic energy. So the mean kinetic energy Ek is going to be equal to 3/2 times kt. As simple as that. A cylinder contains 1.0 mole of an ideal gas. The volume of the cylinder is constant. Calculate the energy required to raise the temperature of the gas by 1.0 Kelvin. A cylinder contains 1 mole. The volume of the cylinder is constant. That means there is no work done. Calculate the energy required to raise the temperature of the gas by 1 Kelvin. So we know that the change in internal energy is equal to Q plus work done. But if the work done remains constant, then the change in internal energy, if the work done is 0 since the volume is constant, the change in internal energy is going to be equal to the amount of heat required now to raise the temperature of the gas by 1 Kelvin. That is, the change in internal energy, remember, is equal to the average kinetic energy of the molecules. The total kinetic energy of the molecules. So this will be equal to, the change in internal energy will be equal to the change in kinetic energy of all the molecules. Remember, this was for just one molecule. So this will be equal to 3 over 2 K times change in temperature. But remember, this was for one molecule, so I will say times the number of molecules, N. So now it becomes a matter of substitution. I'm now substituting. So this will be equal to 3 over 2 times K, which is 1.38 times 10 power negative 23 times the change in the temperature, because they said raises the temperature of the gas by 1 Kelvin. So the change in temperature is 1.0. And the number of molecules, this one can be given by the number of moles times Avogadro's number. Remember, number of molecules is number of moles times Avogadro's number. So the number of moles has been given as, it is, I think, 1 mole. So this will be times 1.0, because we are dealing with 1 mole, times Avogadro's number, 6.02 times 10 power 23. So we press our calculator. Okay, so the energy which I'm getting here is 2240 joules to 3 significant figures. 2230 joules, 22340 joules to 3 significant figures. Alternatively, we would also find this energy from a simple relationship. Energy will be equal to, now, instead of saying 3 over 2K change in temperature times that, I can remove N and K. Remember, N is number of moles times Avogadro's number. And yet K is R over NA. So it means when I multiply K by N, I multiply these two, this becomes N times R. So this becomes 3 over 2 times, I've removed the K, change in temperature, times N times R. This will give us 3 over 2 times 1.0 times number of moles is still 1.0 times molar gas constant, that is, oh no, I think I missed out something on the change in temperature. Capture the energy required to raise the temperature of the gas by 1 Kelvin. The change in temperature was, no. So this would be times R, which is 8.314. Let's try to check this. The number of moles, 1 mole, molar gas constant. So 3 divided by 2 times 8.31. Then times, oh, sorry. I think I pressed this wrongly, substituted wrong quantities. This is giving me 12.5. 12.5 joules. This is also giving me 12.5 joules. This is the energy, 12.5 joules. Okay, so you could have used this expression here or use this. This is easy. I just look at this expression, I remove K times N. K times N, I multiply these two as a mathematician. Notice that when you multiply N times NA and multiply it by R over NA, you remain with N times R. So when you substitute, you get this. You substitute the quantities. This was 8.1, 8.31, 8.31. Yeah. Okay, so let's continue. The volume of the cylinder is now allowed to increase so that the gas remains at a constant pressure. Volume increases, work done is negative. The pressure is remaining constant. Explain whether the energy required to raise the temperature of the gas by 1 Kelvin is now different from your answer. The volume is now allowed to increase so that the gas remains at constant pressure when it is heated. Explain whether the energy required to raise the temperature of the gas by 1 Kelvin, I think that is the heat capacity, is now different from your answer in Roman 1. I think the energy needed to do the work, because now the gas is expanding, so it means more work is done against the atmosphere to push it back at the atmosphere. So it means total energy required is going to be greater. So energy is needed to do work. Energy is needed to do work against the atmosphere because the gas is expanding. That is specific to push back at the atmosphere. And if that is true, then it means the total energy is going to be greater than the one that we have there. So the total energy required, because part of it is used to do work, it means the total energy required is going to be greater. The total energy required is now going to be greater. Okay, state what is meant by internal energy. You find this question almost on every page so that you become confident with it. This is the sum of the random distribution. The sum of the random distribution of the potential, energy, and kinetic energy of the molecules making up a system. The sum of the random distribution of the potential energy and the kinetic energy of the molecules making up the system. That is what we call internal energy of a system. Okay, next. Explain why for an ideal gas the internal energy is equal to the total kinetic energy of the molecules. That one you should now be familiar with it. For an ideal gas, there is no intermolecular forces. So for ideal gas, no intermolecular forces. And if there are no intermolecular forces, then there is no potential energy. And if there are no potential energy, if there is no potential energy, then it means our internal energy is simply depending on kinetic energy. So only kinetic energy of molecules. So only kinetic energy contributes to internal energy. So for an ideal gas, intermolecular forces are negligible, so the potential energy component boils down to zero. It's only the kinetic energy component which contributes to the internal energy. It's only the potential energy component which contributes to the internal energy of the gas. Okay. Next, the mean kinetic energy, EK, of a molecule is given by that expression. K is Boltzmann's constant, T is thermodynamic temperature. A cylinder contains 1 mole of ideal gas. The gas is heated so that the temperature changes from 280 Kelvin to 460 Kelvin. Remember, for an ideal gas, the change in internal energy is equal to the total kinetic energy of the molecules. So here they are saying calculate the change in total kinetic energy of the molecules. Calculate the change in total kinetic energy of the molecules. So the change in kinetic energy of the molecules is going to be 3 divided by 2K times the change in temperature. That is for one molecule, but this will be times the number of molecules. So when I substitute, this will be 3 over 2. K is 1.38 times 10 power negative 23 times the difference in temperature. The difference in temperature is going to be equal to, that is 460 minus 280. Then N, remember N is the number of moles times Avogadro's number. Since it is 1 mole, this will be times 1.0 times 6.02 times 10 power 23. I can press my calculator very fast. This is minus. Okay, so this is the one which is giving me 222.40. And we can use a different method. This energy can still be equal to 3 over 2 K change in temperature times N. But remember, if N is equal to number of moles times Avogadro's number, and K was equal to R over Avogadro's number, so K times N, I multiply these two, I remain with N times R. So this will be 3 over 2 times change in temperature times 3, times the number of moles times R. So we substitute 3 over 2. Change in temperature is 460 minus 280 Kelvin, 1.0 moles times R, which is 8.31. Let's try to check again. So 460 minus 280 times 8.31 times 3 divided by 2. So I get 224, 3.7. So we just round off to 2240. Okay, I think that is warm and dry. Next, during the heating, the gas expands doing 1.5 times 10 power 3 joules of work. State the first law of thermodynamics. Use the law and your answer in Roman 1 to determine the total energy supplied to the gas. So first of all, they said state the first law of thermodynamics. That is increase in internal energy. I can use the positive values only. So that is increase in internal energy. Increase in internal energy. The increase in internal energy is equal to the heat supplied or heating of the system. That is heat added to the system plus the work done on the system. Increase in internal energy is equal to the heating of the system plus the work done on the system. Heat added to the system plus the work done on the system. In other words, change in internal energy is equal to Q plus W. So during the heating, the gas expands, doing work of that. That means work done is negative. This one is going to be negative. Okay? But then the change in internal energy is equal to the change in the total kinetic energy of the gas molecules. The change in internal energy is equal to the change in the total kinetic energy of the gas molecules, which we have calculated above. So that means 240, that is the change in internal energy, is going to be equal to the heat supplied or energy supplied plus the work done, which is negative 1.5 times 10 power 3. In other words, the energy supplied, the Q, is going to be equal to 2240 plus 1500. And this gives you 3700 and that is 40. So the total energy is 3740. I want you to note that the change in internal energy is equal to the heat supplied plus the work done. Heat is supplied, and this heat supplied is equal to the total change in kinetic energy. But then, remember initially, the gas expanded. During the heating, the gas expanded, so the work done was negative. So that's why when we substitute, we come up with this value here. Okay, that is true. Next, state what is meant by an ideal gas. An ideal gas is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures. Then we can define all the terms. So this one is a gas which obeys. It's a gas which obeys PV is equal to nRT. So this one obeys PV is equal to nRT at all temperatures and pressures. So PV is equal to nRT, where P is pressure of the gas, V is volume of the gas, then T is absolute temperature, and of course nR is constant. So this is true at all temperatures and pressures. Any gas which obeys this equation at all temperatures and pressures is what we call an ideal gas. Base that equation at all temperatures and pressures. Next, the storage cylinder for an ideal gas has a volume of 3 times 10 power negative 4 meters cubed. The gas is at a temperature of 23 degrees Celsius and at a pressure of 5 times 10 power 7 pascals. Show that the amount of the gas is 6.1, that is the number of moles. So number of moles is equal to PV divided by R times T. Simply substitute, pressure is 5.0 times 10 power 7. The volume is 3.0 times 10 power negative 4. R is 8.31 and T is 23 plus 273, which becomes 296. You can just press your calculator to verify, but I believe this becomes 6.1 mole. Okay. Next, the gas leaks slowly from the cylinder so that after time of 35 days, the pressure has reduced by 0.4%. After 35 days, the pressure has reduced by 0.4%. The temperature remains constant. Calculate the average rate in atoms per second at which the gas atoms escape from the cylinder. So the pressure reduced by 0.4%, and when you look at the formula, you notice that the number of moles is directly proportional, or the amount of a substance is directly proportional to the pressure. So the pressure is directly proportional. The pressure is directly proportional to the amount of substance, or the number of moles is directly proportional to the amount of the gas. So let's first find the loss. The loss is going to be therefore 0.40 divided by 100 times 6.0. Okay, this is 6.1 moles. Because the pressure has reduced by 0.4% and yet it is directly proportional to the amount of the gas, then the loss in the amount of the gas is going to be equal to this one, 0.4 over 100 times that. So this is going to be 0.024 moles. So this is the loss. This is the number of moles which are lost. And if we want this in atoms, if these are the number of, remember 1 mole is equivalent to 6.02 times 10 power 23 atoms. So we can find the loss, the number of atoms lost. Number of atoms or molecules lost. Number of atoms lost, that is going to be 0.024 times 6.02 times 10 power 23 atoms. These are the atoms which are lost. Then we can now find the rate at which they are lost. The rate is going to be number of atoms which are lost. Let me multiply this and I see 0.024. No, this is 0.24, 0.4 divided by 100 times 6.1. This was 0.244. Let me modify this slightly to 3 significant figures. So there is another 4 somewhere there. When I multiply that, I'm getting 1.47 times 10 power 22 atoms divided by the time is 35 days. Time is 35 days because I'm finding the rate, that is, I'm finding N over T. That is the rate. So this is 35 days, that is 35 times 24 hours times 3,600 seconds. And this gives us the rate. Let me just divide. So this is giving me the rate as 4.9 times 10 power 15 per second. Those are the number of atoms or nuclei which are lost per second, 4.9 times 10 power 15 per second. Okay, so here I said 1 mole is equivalent to that number of atoms. So how many atoms are lost in that are equivalent that number of moles? That's what I try to find out. Okay, next. The mass of the aluminium cup in B is 6.2 grams. The specific capacity of aluminium is 910 joules per kilogram per Kelvin. The energy in B is transferred to the cup. The energy in B is transferred to the cup. Calculate the mean rise in temperature. Calculate the mean rise in the temperature of the cup. Okay, so we have that the energy Q is going to be equal to mass, specific capacity times change in temperature. Now Q, I remove the question which involved the Q. I'll just quote it here. The amount in B, the energy was, I removed the part which was required in finding the energy, so I'll just quote it here. The energy I calculated it, I think it was 4.8 times 10 power negative 3 joules. That was the energy in B Roman 2. So we just want to find calculate the mean rise in temperature of the cup. So 4.8 times 10 power negative 3 is the amount of energy. Should be equal to the mass, which is 6.2 grams. That is 6.2 times 10 power negative 3. Specific capacity is 910. Change in temperature, delta theta. So when you simplify delta theta, okay. So this delta theta is 8.5 times 10 power negative 4. 8.5 times 10 power negative 4. Of course, one part of the question which was actually requiring the energy which is lost. That one is you just get the rate, the number of nuclei, and you multiply it by the energy of just one molecule, which is 3 over 2 K times T. That one gives you the energy. So I just skipped that because we calculated several times. Change in internal energy is equal to Q, which was the total kinetic energy of the molecules. For one molecule, it was 3 over 2 times K times T, and this, when I multiply this by the number of molecules, that would give me the total energy. This is what gave us 4.8, so we don't need to calculate that again. So that gives us the value of K. And maybe I can stop here because my battery is down. Let's stop on this one, I think. Okay, we shall start part 3. This is part 2. Part 3 will start from this question here. Part